Okay, hello and welcome back everybody. I'm calling this section the complex numbers and algebra. That is to say the complex algebra. And you'll recall maybe from the very first video that the definition of algebra is a set endowed with a multiplication. So the fact that we have a well-defined notion of multiplication on the complex numbers is why we call this the complex algebra as well. But I just want to let's motivate the complex numbers first, because I think a lot of people don't give enough credit to what the complex numbers actually do for us. I think a lot of people, because we use this word, the imaginary number, they're not imaginary at all. They're just as real as any other number that we use, except perhaps the positive whole numbers, right? The natural numbers. I mean, it's really natural for humans to quantify things with whole numbers. You have 1 dog, 2 dogs, 3 dogs. But even the moment you get to negative numbers, to 0, to fractions, what is 4/5 of a dog? Well, it's a natural thing to think about, but probably only because you've been learning about it your entire life. And imaginary numbers are just the same. You could either argue all numbers are real or all numbers are imaginary, and I guess I'm probably actually in the camp that all numbers are imaginary. But with that said, imaginary numbers are no less imaginary than other numbers. Maybe I'll rewrite that here. Or no more imaginary than, I'll say, most other numbers. And I'll give you a reason why. My favorite reason why is just that we will find out a few times this course that this imaginary number I, which is the one that, satisfying I squared equals -1, that imaginary number really is just a representation, an efficient representation of rotation by 90 degrees, or equivalently pi over 2 radians. That's all it is. So I guess arguably if you only want to live in one dimension, then you could say it's more imaginary than anything else. But the moment you decide you live in dimension greater than 1, so 2, 3, and so on, then you have access to 90-degree rotations. And the moment you have access to 90-degree rotations, that is literally what the imaginary number represents. I don't think enough people stress that when they talk about I, that it really is just a representation by 90 degrees. There are a couple ways of thinking about it. The easiest one for Y is you've got the number 1 over here, the number -1 over here. And if you multiply, let's say multiply by -1, you start here and you end up over there, but a half multiplication would be equivalent to 2 half multiplications. Half mult gives -1. So I'm going to take 2 steps to get to -1. You can think about moving from 1 to -1 as a 180-degree rotation, and then a half multiplication by -1. This is going to be a 90-degree rotation. And that's going to give you, we're going to see this later, that'll be a representation of I for us in kind of the 2-dimensional plane. So that's maybe the easiest way to motivate it. As long as you're content with 90-degree rotations, you should be content with I. Certainly you can live in 1 dimension if you want to, but most of us live in 3, 4 if you include time. And another motivation is just the Schrodinger equation itself, and I brought this up from the beginning. So the Schrodinger equation is, by definition, I h bar d dt psi equals h hat psi. And what do you know? It's there. You can't avoid it. But that's maybe, that's contrived, because it's like, okay, so why did Schrodinger put it in his equation in the first place? Well, there's a very good reason why, and it does correspond to rotation by 90 degrees. It equivalently corresponds to the fact that waves, right, the real world being made of waves represent reality. And in fact, they represent reality even on the quantum scale. So this is, in some ways, quantum mechanics was kind of, it's mechanics where when you zoom infinitely far, I shouldn't say infinitely far, when you zoom in as far as humans have the current ability to zoom in on the physical world, everything behaves like waves. So that's really what quantum mechanics is. It's just zooming in as far as we can on the real world, and we find out that everything behaves like waves. And let's look at a specific property of a couple notorious waves. Both sine x and cosine x are our classic wave functions. That's with a space between the two of them, because interestingly enough, that psi is called a wave function without a space between it, but wave space functions. And they satisfy the following identity. If I take a derivative twice, right, d dx squared, so two derivatives of sine gives me negative sine. Two derivatives of cosine gives me negative cosine. And so what do waves, what is kind of the true representation of a wave? It's doing something twice. D dx squared is a negative sign. Doing something twice is a negative sign. So in some ways, and we'll see this in reality, we'll see what it actually means when I'm highlighting what I'm highlighting really towards the end of this semester. It's going to take us a while to make this comparison explicit, but in some ways, d dx, so if d dx squared equals -1, that's what that multiplication is right there, multiplication by -1, then d dx, a regular derivative, equals I, so far as waves are concerned. So it turns out that in some sense derivatives of waves are the imaginary number. It's multiplication by the imaginary number. And like I said, it's going to take us a while to make this explicit. It'll be towards the end of our semester, but that really is so many reasons why the imaginary numbers are important. And in fact, it's all related to that 90-degree rotation. The fact that, I mean, where's the 90-degree rotation here? Or pi over 2, because let's take a derivative of sine. It's cosine. You all remember this from calculus, but by the way, cosine is the same as x plus pi over 2. Or equivalently, sine x plus 90 degrees. There is your rotation by I, or rotation by 90 degrees. So it's built in, right? And we could do the same thing with cosine, right? d dx of cosine is negative sine, which by the way is cosine of x plus pi over 2. So really, you know, these derivatives, multiplication by I, rotation by pi over 2, etc., these are all the same object, and they all are the imaginary number. So definitely not imaginary as long as you're content with waves. Even Schrodinger's equation, I know that one is maybe feels a little bit more abstract. Rotation by 90, though, they're all real, perfectly real objects to work with. Now, to that end, that's really a reason why complex numbers are ubiquitous in quantum mechanics. You cannot avoid them in quantum mechanics because of all this interaction with waves. I do want to mention the reason why mathematicians care about the complex numbers, and that is the fundamental theorem of algebra. The fundamental theorem of algebra is fairly easy to state. It just says any nth degree polynomial, and maybe it's been a while since you've seen those words, so what does that mean? This is just something like a sub n, that's a coefficient by the way, x to the nth power plus a sub n minus 1, just another coefficient, x to the n minus 1 power plus dot 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 plus a sub 1, x to the first power plus a sub 0, x to the 0th power, by the way that's constants. So those are those n degree polynomials, and I just want to make it clear that all these a's are just coefficients. A for arbitrary coefficients. So something could be like, 3x squared minus 2x plus 1. That's, for example. So the 3, the negative 2, and the 1 are those coefficients there. So what does the fundamental theorem of algebra say? It says any nth degree polynomial has exactly n roots up through multiplicity. And if you don't recall what multiplicity means, it just means that the root has instead of passing through, if you looked at the graph, instead of passing through the axis, there's a root, there's a root, and there's a root, a second order multiplicity root would just touch the axis and then pull back. So all the even order multiplicities touch and come back. This would be odd multiplicity, even multiplicity. So they just, you can count the multiplicity of any given root, but once you do count those multiplicities, an nth degree polynomial has n roots, but those roots are complex valued. So that's what the fundamental theorem of algebra says. We cannot get into a proof. If you want to see one, reach out and I can share a proof with you. But that is the definition of the fundamental theorem of algebra. This is why mathematicians care, because it gives a consequence is that all polynomials are n, so nth degree polynomials are n times factorable, so long as you find the roots. So you write something like an x to the n plus an x minus 1 plus dot 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 plus a1 x1 plus a0 x0. You can actually write it as a product now, x minus b1, x minus b2, x minus b3, dot dot dot, x minus bn. And technically the an comes along for the ride, but you don't worry too much about that. So these are the roots, and you can just factor the polynomial into those n terms. Mathematicians care about that because once you put it in factored form, your life gets so easy. It's just like, it changes the entire behavior of your world when you put it in factored form. So that's really why mathematicians care. And we will need to use this periodically in this course, this fundamental theorem. I will just refer to it and I'll say, by the way, remember when we introduced complex analysis and I said the fundamental theorem of algebra was important? Yeah, so it just means that we can factor or find our n roots or whatever. That's why mathematicians are going to care. But let's actually get into kind of the nitty-gritty details of the complex numbers. So those details, let's just define them. And I know I already did a couple of videos ago. Let's define the complex numbers. So we use the symbol C, the second stroke on the left-hand side, and they are defined by the set x plus I, y, such that x and y are in the real numbers, and I squared is just defined to be -1. So that's the complex numbers for you. And let's just do a couple really quick examples of these. So 6 minus I, 4 plus 3i, 2 minus the square root of 2i, 1 plus e times I, pi minus pi I, etc. This could go on forever. Grab your favorite two real numbers, add an I to one of them, and sum them together, and you'll get a complex number. So that's what the complex numbers look like. And in fact, this form right here is called, there's a couple names for it. I think the regular way people say is standard form, but we have a lot of names. So this is standard, Cartesian, normal, or even regular form of a complex number. We'll see that there are some other forms that complex numbers can take, but in general, we'll refer to this as the standard form or the Cartesian form. I do like the Cartesian form for this name as well. Let's talk about the operations, which is the same as the algebra that I mentioned before. We have our favorite cases of addition, subtraction, multiplication, and division. What do you know? Not really a surprise there. Given by everything you would expect. x1 plus I, y1, and we're going to add that to x2 plus I, y2. And it's not a huge surprise what we're going to do. We're going to combine these terms, combine terms without I, and we're going to combine the terms with an I. So fairly straightforward. I'm just combining x1 plus x2 plus I, y1 plus y2. Not a huge surprise. We can do subtraction as well. x1 plus I, y1 minus x2 plus I, y2. Let's just make sure you keep the minus sign on the same terms that it's associated to, so both the double terms here, the x2 and y2 terms. So we'll have x1 minus x2 plus I, y1 minus y2. So let's look at two examples on the right-hand side of both of these. These are kind of the easy ones, by the way, before we get to multiplication and division. The easy ones. So let's do 3 plus I plus 6 minus 4i. All I'm going to do is look. 3 plus 6 gives me 9. There's really a 1 here and a -4 there. So 1 minus 4 is -3i. So that's how you're going to do that. First round of addition. Let's do a round of subtraction. 1 minus 2i minus 3 minus 4i equals, let's combine the 1 minus 3, gives me -2. Let's combine -2 minus -4, so really plus 4. -2 plus 4 is plus 2i. It's really not too bad when you're doing addition and subtraction. When we get over to multiplication and division, our life gets a little trickier. So multiplication is going to behave like foiling, which is kind of what you would expect. The way these happen to always be written out. So let's write it as a multiplication, x2 plus I, y2. We need to FOIL. So break out those algebra brains. That's why it's called the complex algebra. So to FOIL, first, outside, inside, last. And I'll mention it's FOIL and recall I squared equals -1. So you're going to want to keep that in mind, that I squared is -1 when you FOIL everything out. Let's go ahead and do it. The first gives me x1, x2. The outside gives me I, x1, y2. The inside gives me I, y1, x2. And the last gives me I squared, right? Because both terms at the end there, both iy1 and iy2, have an I on them. And so I multiply, I get I squared, y1, y2. And because I squared is negative 1, we can simplify everything a little bit because we can combine these like terms. And the negative 1 also lets us combine. So if we combine all of those together, we get the real terms, right? If I'm putting this into normal form, the real terms are x1, x2 minus 1 times y1, y2. So x1, x2 minus y1, y2. The terms with the I on them, if I'm putting it in normal form, are x1, y2 plus y1, x2. So you'll notice we ended up with a minus sign there and a plus sign there. And that's going to be important throughout the whole semester when we FOIL these, to not forget that. So that's going to be multiplication. Let's look at an example really quick. 3 plus I, negative 4 minus I. If I want to FOIL these out, you could just go ahead and identify x1, x2, y1, and y2, and then use that as a formula, but I actually like to FOIL it out every time I see it. It's actually easier for me to just go ahead and FOIL. So I do 3 times negative 4, that's negative 12. I do outside 3 times negative I is minus 3i. I do the inside, I times negative 4 is negative 4i. And I do the last, which is I times negative I. So there's a negative, right? Negative I squared. And then just don't forget that I squared itself is negative 1. So I have a negative, negative 1 happening, which means overall, what do I have? I have 12 minus negative 1. 12 minus negative 1 is 12 plus 1 is, or negative 12 plus 1 is negative 11. And then here I've got negative 3i minus 4i. So negative 3 minus 4 is negative 7i. And so that's going to be the example of a multiplication. Like I said, it gets a little bit trickier. And then finally, division also gets fairly tricky. Let's look at division really quick. So division, if I'm going to, and division, by the way, is the same as a fraction. In general, you're going to benefit always by looking at fractions here. So let's look at a fraction here. x1 plus I y1 divided by x2 plus I y2. And you could always leave the fraction like that, but in general, I mean to say put it in normal form. So let's say to put into standard form, we must multiply top and bottom by something called the complex conjugate. Now that's going to be a new word for us. Complex conjugate. What does this mean? Turn all i's to minus i's. That's all it means to do a complex conjugate. You see an I, you're going to replace it with minus I. So to put this in standard form, we are going to multiply the top and bottom by the complex conjugate of the bottom. This is equivalent to rationalizing the denominator, which is something you did probably back in 7th grade. It's actually equivalent to that, because if you end up having square roots in the denominator, you have square roots of negative 1 in the denominator, you try to rationalize it, you would do exactly this process. So you'll recall from way back when you would rationalize the denominator. In this case, we're not rationalizing, we are realizing. So in this case, realizing in the sense of making real, right? Making real. You'll see why. So let's actually do what I just described. To put this in standard form, we must multiply top and bottom by complex conjugate of bottom, where we're turning all i's to negative i's. Okay, let's actually do that. Read it out and then follow directions. x1 plus I y1 divided by x2 plus I y2. Multiply top and bottom by complex conjugate of bottom. The complex conjugate of the bottom. I'm replacing the I in the bottom with a minus I. So let's do it. x2 minus I y2. x2 minus I y2. Now you'll notice I can get away with this because that is just equal to 1. Right? So I've multiplied by 1, but I've done it in a very particular way, where now I have to play FOIL games. Play FOIL games on numerator and denominator. Lucky, lucky us. Time to play FOIL games, everyone. Okay, so with that said, numerator, FOIL games, let's go. x1 times x2, that's my first. So I have x1, x2. I have the outside, I have x1, negative I, y2, so minus I, x1, y2. I've got the inside, I've got I, y1, x2. So I've got plus I, y1, x2, and I've got the last I, y1, minus I, y2. So I have a negative sign coming for free, negative I squared, y1, y2. I then have the entire denominator to play FOIL games with. x2, x2. It gives me x2 squared. I have outside x, so minus I x2 y2. I have the inside, I have a plus I x2 y2, and I have the last negative I squared y2 squared. If I do everything correctly with these FOIL games, I should end up with a real denominator. Everything should be realized. Okay, so look at the denominator. What's going on? I've got negative I x2 y2 plus I x2 y2. Those are canceling. Here I've got negative I squared. Negative I squared is negative 1, so positive 1. So I have x2 squared plus y2 squared in the denominator. And that is a real number. There are no i's sitting around anymore. The numerator, I just kind of have to combine terms that are lucky. So there's negative I squared, also known as positive 1. And so I have x1, x2 plus y1, y2. And then I end up with a positive I y1, x2. So I y1, x2. I have a minus I x1, y2. It's not quite in normal form or standard form yet, but we're almost there. Almost there. The standard form is me distributing the denominator to both terms in the numerator. Distribute denominator. So once I distribute it, I have my normal form. The normal form is not great. x1, x2 plus y1, y2 divided by x2 squared plus y2 squared plus I, right, because I've distributed to the second term that has an I on it. Look at my second term, it's y1, x2 minus x1, y2 divided by x1 squared plus y1 squared. So that is my standard form of division. So basically, if you want to make your life easy, pause the video now, write that this is supposed to be equal to this if you're doing it in normal form. Not great, not the world's best thing. It's what we've got though. So that's what you're going to want to think about when you're doing the complex algebra, all three of these cases. I'm not going to go through an example of this last one. We can maybe save that for the next video. But we are going to move on to some other kind of natural notions with the complex numbers, because if I don't cover these, then I'll have to cover them eventually. And we have some new notations. And in fact, you've already seen one of these. The first is the complex conjugate. Okay, so what is the complex conjugate? This is notated by a bar, like an overhead bar sort of shape. So if I have x plus iy, I put a little bar above it, and it's defined by x minus iy. Sometimes other authors will use a star instead, so they'll use, or like an asterisk, right? So they'll use an asterisk, and that's going to be the same. So the conjugate just means you replace an I with a minus I. Let's say that over here, replace each I with minus I. That's all the complex conjugate means. We also have a notion of the complex magnitude. And often I'll just call this the magnitude itself. I won't call it complex magnitude. This is denoted by vertical strokes, just like the absolute value. So you've got x plus iy. If I put vertical strokes on either side, that's going to be equal to the square root of x squared plus y squared. And this kind of goes back to if you were calculating magnitudes or the distance formula of anything else in 2 dimensions. You would add each component squared together. Now it turns out the magnitude is also equal to, this is x plus iy times its conjugate. So there's this notion of taking the square root of something times its conjugate, and actually I'll notate the conjugate by that horizontal line the way it's supposed to be noted. So it's x plus iy, and so that's going to be equivalent to the magnitude. And then finally, actually maybe I'll mention over here the complex magnitude as quote-unquote distance from 0, which happens to be 0 plus 0i. So you want to think about it just like the absolute value. It's the distance from 0 of any complex number. And we have 2 other terms, which is the real part. And we denote the real part with an RE, and then I usually use a square bracket, but some people use a parentheses, x plus iy. This is just extracting the number x, and we have something called the imaginary part, which is denoted by an im. And you just extract y. Now, something that confuses a lot of students is that there's no I here. Okay, so you really want to be certain that for some reason, this is just the way we defined it. It's totally fine. You drop the I when you take the imaginary part. Like the x disappears, but the I also disappears. We're just asking about kind of the coefficient of I for the imaginary part. So that can kind of screw people up now and then, just because they kind of forget that they're supposed to drop the I from the imaginary part term as well. We'll cover examples of all those in the next video. Those are fairly straightforward. They're not nearly as hard as the multiplication or the division. The last thing that I'm planning on covering is how do we plot these? So let's say plotting complex numbers. And then we'll do polar form, complex numbers, and Euler's formula. That's kind of the last section we're going to cover here. So you can plot a complex number in 2 dimensions as something like the xy plane is still the xy plane, but because x is the real part, we just defined it as the real part of our complex number, and we just defined y as the imaginary part of the complex number. Then what you can think about is that actually this is the real axis r, and then this is the imaginary axis I times r. And then you call the entire thing the complex plane, because it is a 2-dimensional plane, C, which happens to be equal to r plus I r. So you can plot numbers on there. And let's actually do a couple explicit examples. So if I did something like 3 minus I, you start at 0, 0. This is still the point 0 plus 0 I. 3 would be like 1, 2, 3. Minus I would be a negative number in the I direction. This is 3 minus I. You could do something like negative 2 plus 2I. And you would just go to left, 1, 2. You would add 2I to that, 1, 2. There's your negative 2 plus 2I. And so you can plot so many other points. Let's just do one more. Let's do 1 plus 2I. We move to the right 1, we go up 2I. There's 1 plus 2I. So that's what it would mean to just kind of plot complex numbers on a 2-dimensional plane. And then I have this thing called polar form. What is polar form? Polar form is a way of representing x plus iy as a radius and then an angle. So you represent that number, which is just r, the real number plus an imaginary number, as a radius. So that's away from 0, and an angle, theta, from positive x-axis, or the positive real axis. Don't worry about the e and the I right now. It's not too important, but that is the way that the polar form is written. And the way we can think about it is, what I can write over here is that there's some sort of radius there for 3 minus I, and there's also an angle away from the x-axis. There's a radius for 1 plus 2I, and there's also an angle away from the x-axis. There's a radius here, and there's an angle from the x-axis. And so that's why it's called polar form, because the x-axis behaves like a pole. Like if you were looking at the globe, kind of the North Pole on the globe, you see like these concentric circles radiating out from the North Pole. So it's called polar form because of that. And the thetas act along the circles themselves, and the radius kind of tells you how many circles you travel in. And it's really easy actually to convert. The process of converting is really easy. You can, instead of writing it as r e to the I theta for x plus iy, what you actually write is x plus iy is the radius, it's just the magnitude, so that's x squared plus y squared. And the angle is always going to be the inverse tangent of y over x. Now, that can be multi-valued. I'll talk about what that means in the next video for when that is multi-valued. I'll say it can be multi-valued. Be careful. But aside from that tiny thing that we'll cover in the next video about that being multi-valued, you can just translate really easy back and forth x and y, and then x and y. So you've got those 3 cases of x and y that show up. That's how you convert to polar form. And in fact, if you want to go in the other direction, suppose I started with r e to the I theta, you can actually go in the other direction pretty easy too. What you get is r cosine theta plus I r sine theta. And so you can also go in the other direction, or if you know r and theta, you know your radius and how far you are from the x-axis, you can go back into your standard form. And then this was your polar form. Finally, I do want to talk about Euler's formula. Is the polar form of r equals 1. Euler's formula is just the polar form of the entire circle, so that's the unit circle, because if I take my complex plane and I construct the r equals 1 circle, there's my r equals 1 circle, then that's the unit circle, and the amount that I've traveled, some theta, can be represented as the following. E to the I theta, there's no r out front because r is equal to 1, is cosine theta plus I sine theta. We will prove this eventually. But for now, I just want you to take it as my word, and then, wait a week or two and you'll end up being able to prove it. So this is just a very nice formula that you've seen written quite often, and you've probably seen it written as e to the I pi plus 1 equals 0. This is because if I put pi in for cosine and sine, what do I get? I get cosine pi plus I sine pi plus 1 equals -1 plus I times 0 plus 1 equals 0. And so that is Euler's formula. It's a really very elegant formula that people will talk about all the time. We're going to see its consequences the rest of the semester. So I'm going to stop there because I've really kind of thrown everything at once at you. And so I just kind of want you to sleep on this, digest it, and then we'll talk about more later. See you then. Bye.